Hi, I'm Dan Estrada. It is March 18th, a Saturday. This is the Saturday at the end of spring break. Classes start on Monday. Um, and we are in lesson 9, so let's go ahead and jump into the class. Here we go. Yeah, so we're on lesson 9. The lesson this week is on climate change and geoengineering. So I want to talk to you a little bit about climate change. I don't want to just convince you that it is happening. Hopefully everyone agrees that it's happening. I want us to think this week about the um, not just the engineering challenges of climate change, but also the ethical dimensions of this challenge. So my goal for this video is to talk to you a little bit about the history of temperature on the planet, to put in context the recent bout of climate change. And then the other big lesson this week is on geoengineering. So my friend John Lawhead had a postdoc at USC last year on geoengineering, and he did a video. Here's John giving his lecture. I'm not going to repeat his lecture. I'd like you to watch him actually give the lecture, but he's going to walk through this slideshow on climate change and geoengineering. Uh, so, uh, so we'll talk a little bit this week about the ethical dimensions of climate change and whether geoengineering is ever an ethical project. So your task this week is to treat this a little bit like a case study, but sort of very open-ended. You can talk about the engineering challenges, you can talk about the ethical challenges, you can talk about the desperate circumstances that we're in, the political challenges. There's lots of things to talk about with respect to climate change. This is really the major problem that humanity faces in this century, and this is affecting us today. So it's a big issue. I have lots of things to say about it. This is lesson 9. Let me just do a couple of housekeeping things. This is lesson 9. Lesson 10 is your first research project week. So you need to have done some library research, come up with an annotated bibliography, and present your research for lesson 10. This should be on a case study of your own choosing. I give some examples of case studies, but you can pick your own case studies. On your own, it'll be the same case that you use for lessons 10 and 11. You want to pick those cases now and start doing research now to get started on that. This lesson is a little bit of getting back into the pace of things before we start in lesson 10 after spring break. Lesson 10 and 11 is research project weeks, and then after that we have a unit on artificial intelligence. Where I'll be talking about the history of artificial intelligence and also the ethical challenges that it presents, both from an economic and political perspective, but also from a social perspective. Okay, your replies from lesson 8, which was due before spring break, will be due on Tuesday of this week. So you still have time to do the replies from last lesson. And then I will have a hangout for lesson 9 on Tuesday. All right, I'm going to go ahead and start the lesson. So, climate change, it's a fact that the planet is getting hotter. Here's a nice little graphic that shows you over the last 100 years of climate change. And the fact that the planet is getting hotter is really closely linked with human industrial activity over the last 150 years. And it's recently hit a tipping point where things are getting very hot very fast. We're on pace to pass 1.5°C average global temperature change in the very near future, and we're on pace to hit at least 2 degrees Celsius by the end of the century. 2 degrees increase temperature change it's a big deal. We'll have major problems with things like growing crops and where we can live, habitable regions. After 2 degrees centigrade. And in addition to extreme weather, we'll also have extreme weather events, more hurricanes, more tornadoes. This will cause more and more damage. Sea levels rise, coastal cities get flooded. This is going to be huge infrastructural problems. And then all the political and economic chaos that results from this damage. So this is, it's really a challenge for all of humanity. We don't yet have the resources for properly dealing with it. We have some tools and technologies that are promising, but our political infrastructure is just not where it needs to be. And our current president is not making it any better. So it's a big challenge. It's a very serious challenge. And what I want to do is so not just convince you that it exists, but I want to give you a little bit of an idea of how to think about it by talking about the history of climate change from the beginning of the planet. So the first thing to say is the planet's getting hotter. So we're getting more hot weather, but we also just had a blizzard in March. So we know that it's not always getting warmer, and we have these extreme cold events. In fact, the New England area up here seems to be frequently impacted by destabilization of the polar ice cap. So because the polar ice cap is basically melted by now, there's not a lot of ice up there to keep the cold stable, and so there's a big sort of wobbly vortex, and the wobble brings cold air down this far, this late into the year. Meanwhile, we're having things like tornadoes. It's already tornado season in the Midwest, causing lots of damage. So the important thing to know is that climate, when you say global warming, means the whole temperature shift is getting hotter. Right? So it's the whole, I don't really need to tell engineers how to read a graph, but the whole curve gets hotter. So we have more extreme weather events. Most of the weather events are exactly the same, though, right? Everything in the average is going to feel like any other day. We're also going to get fewer extreme cold events. The whole thing shifts. But it's not just that things are getting warmer. It's that things are getting less stable. Climate systems are getting less stable. They're getting less predictable. We depend as human beings on predictable weather for our food and for our well-being. And as that gets unstable, it becomes problems for us. But in general, things are getting warmer, and the reason things are getting warmer is from atmospheric carbon, and human beings are almost entirely responsible for the radical change in atmospheric carbon over the last 150 years, almost entirely from industrial activity. There's very little sense in denying the facts, but there are other explanations people offer for why climate might change. Changes to the Earth's orbit. You can see that changes to the Earth's orbit can't explain changes to the temperature. Changes to solar activity. The sun is actually one of the most stable objects in the solar system. It's one of the most rounded objects in the solar system, one of the most stable objects in the solar system. And it has changed very little over the last 150 years. Can't explain change in temperature. Volcanic activity will be relevant. All these things will be relevant when we talk about geoengineering, because when we're operating on geosystems, these are some of the tools we will use to operate on geosystems to try to mitigate the effects of climate change. But volcanic activity has not been at a level that explains rises in temperature. All of these together can't explain it. The only thing that actually explains here's changes in land use, like deforestation, doesn't explain changes in ozone. We also release lots of aerosols, little microparticles. In fact, aerosols lead to a kind of global cooling, and this is one of the techniques that people have talked about to change the effect of climate change. If we release the right sort of aerosols into the atmosphere, will that offset the impact of climate change? But there are reasons to be skeptical of this. We'll talk about this when we get to geoengineering. So none of those things explain it. The only thing that actually explains the change are the change in greenhouse gases. Those have increased dramatically over the last 150 years, almost entirely due to human industrial activity. And it fits very nicely along the curve of observed temperature change. So here's a video from NASA. I won't play this whole thing, but this is a computer simulation, a very extensive computer simulation. Actually, let me turn off my camera also. Oops. So you can see the whole thing. Yeah, so it's a very extensive computer simulation of 2006 in climate change. So here the red is, so this is carbon in the atmosphere. So the red here is carbon dioxide. The darker red it is, the more carbon in the atmosphere. You can see that most of the carbon is coming from the Northeast and California in the US, some places here in South America and Central Africa. Lots of activity, especially at the beginning. It's easier to see here in Europe, and then out in China and Japan, Southeast Asia. You can see that the change in atmospheric carbon is almost entirely confined here to the northern hemisphere. This is why the Arctic ice cap has basically melted, and all this carbon sort of stays in the atmosphere, and it directly relates to global warming. If you haven't heard it 1,000 times by now, right, the carbon is a greenhouse gas, and that means that the sun rays that pass through the carbon end up staying there because the sunlight sort of bounces between the carbon and the atmosphere. So what you see here, this is June, when all the plants bloom and all the plants are out in the when all the plants are in bloom, they suck all the carbon out of the atmosphere. So it was red, it was very red, and then that red almost went away because all the plants in bloom during the spring and summer have sucked all the carbon out of the atmosphere. Now mostly what's left is carbon monoxide. The plants don't breathe carbon monoxide, so that stays out in the atmosphere. And then this cycle repeats itself. It's a very beautiful computer simulation using very sophisticated data. This is NASA data, and the funding for NASA to continue doing this kind of research has been severely gutted. So this is a global picture of what's happening with the climate, and these are things that we haven't had until very recently because of advances in computer science and because of radical advances in our climate science. And images like this help us understand how the climate system works as a system. So this is my goal today, to try to explain how the whole system works. And I want to do it by explaining the history of temperature. I'm going to be using John Baez's page on temperature. Baez he's a mathematician. He's not a climate scientist. He's a mathematician at UCR. This is University of California, Riverside. This is where I did my undergrad. But on this page, he has this nice compilation of lots of information about the history of climate change. Let me put my camera back up in case anyone likes that. All right. Okay, so and there's lots of neat little graphs, and going through this, I know for me it helped me understand how dramatic our current climate condition is. So putting it in the context of the last 4.5 billion years of Earth's history. Okay, so there's a couple of graphs I want to focus on. I'm not going to go through the whole thing, but just a couple of graphs I want to focus on. So this is the first one. This is all 4.6 billion years. So at the bottom of this graph is 4.6 billion years ago, when the Earth was just a molten ball of rock. We didn't have stable rocks on which life could form. The whole surface was molten for the first billion years. So not until 3.5 billion years ago did the Earth start forming stable crusts, and not until maybe around that time, around 3 billion years ago, did the first life forms emerge. And over this time in the very early Earth, you can see that it went from really hot molten rock to cold, and then hot and cold. It sort of bounces around. And if we just glance throughout the rest of this, you can see that climate, the temperature on the planet goes. So on the right here is warm, and on the left is cold. It starts off very warm, goes cold and warm, and it sort of bounces around. And it doesn't bounce around in any stable pattern. It'd be really nice if it was like a sine wave where it had some regularity to it, and then we would know what to expect in the future. But this is a very complex curve, sort of very difficult to describe, very difficult to understand what could cause temperature change like this. And so one lesson from this is that the Earth has in the past been a lot warmer than it is today, right? So if today's right down the middle, then it has been, in fact, for significant parts of the Earth's history, it's been significantly warmer than it is right now. And for some periods of the Earth's history, it's been significantly colder than it is right now. And in fact, if you look at the chart today, up here at the top, we're kind of in a cooling period. We're sort of on a general cooling trend, and we're in a little bit of a cooling period. And here we're back at center, and we're now going warm again. Now, if you don't know the Earth's history, Cambrian explosion here at 57 million years ago is when there was life on Earth before this, but it didn't really sort of explode and take over the planet until the Cambrian explosion. This is where all the trilobites were and so on. Life radically diversifies during the Cambrian explosion. And you can see that the temperature is sort of moderate, and this a little bit warmer than it is today, for a period a little bit cooler. So life sort of explodes in the Cambrian explosion, and then diversifies. The Carboniferous period is characterized by lots of Carboniferous plants, plants with pulpy material. woody material. Back in the Carboniferous, there weren't organisms that could digest the plants. So these plants with their sort of thick cell walls. So plants sort of took over the planet during the Carboniferous period, and not only did they not have any predators that could eat them, but they didn't also have anything that could break down their bodies after the plants died. And so you would have plants growing and then sort of falling on the ground and not rotting because there were nothing to make it decay, but then more plants growing on top of that and then falling on top of it, sort of just piles of plants. And this piling of plants over millions of years in this period is what is all the fossil fuels that we have today, right? So this large accumulation of biomass, of living biological material, it all gets buried underground and heat and pressure for long periods of time, and you get oil and coal and all the fossil fuels that we use today. They call them fossil fuels because they come from this old, mostly plant, but also animal matter from a long time ago. And it takes millions of years for this biomatter to turn into fossil fuels. And one important thing to understand is that when plants are growing, they're turning the sunlight into they're turning the sunlight and the carbon in the atmosphere into their bodies. So in early Earth, there was lots and lots of carbon in the atmosphere. It was very, very warm. And plants breathe carbon, right? So they take carbon as input, and they use light to turn that carbon using photosynthesis, turn into energy. Use the energy from the light and turn it into food that they can use. Let me say this one more time. Plants take sunlight and atmospheric carbon and turn it into their bodies. Plants are carbon-based life forms. We're all carbon-based life forms. That means we're built out of carbon molecules, and the place you get the carbon is from the atmosphere, carbon dioxide. So plants breathe in the carbon dioxide, turn it into their bodies, and then other animals eat those plants. Eventually we eat those. We either eat the plants, we eat the animals, put that carbon in us, and it becomes us. So we're pulling this carbon from the atmosphere. We're also releasing that carbon back into the atmosphere when we exhale. And not many people know this, but you lose, so if you're working out and you lose weight, the place where you lose this weight is by breathing it out. So when you breathe out carbon dioxide. Carbon's a big, beefy atom. You're breathing out, and oxygen's also a big beefy atom, and that's the weight that you're losing. You're not losing the weight through water, like urination or defecation. Most of the things that you excrete that way is stuff that you put in your body, like the food that you eat. You pass the stuff that you don't use, but most of that is food that you just put in your body. When you lose weight, you don't lose it those ways. You lose it by breathing it out. This is why you breathe more. You're burning more energy. And so you breathe more out, and that's where you lose weight. So most of the weight you lose when you lose weight, you lose through your mouth, through your lungs, by breathing it. The point here is that biological material comes from the carbon in the atmosphere. Plants literally turn that carbon into their bodies, and we eat that. So all of that carbon that's buried in the ground and becomes fossil fuels, you can think of that as stored sunlight. It's stored sun energy. Literally millions of years of stored energy from the sun that plants had been storing in their bodies for millions of years. And it turns into fossil fuels, and we release all of that energy back into the atmosphere in the form of carbon dioxide over the span of just 150 years. Right? So millions of years to put all this carbon in the ground, and all of that energy is released into the atmosphere again in about 150 years. This is the kind of thing that's never happened on the planet before. There's not any historical precedents for it. We'll look at what the historical precedents are. So let me just sort of go through the rest of this graph here. So Carboniferous period, it got cool. In fact, in some of these cooling periods, actually the Earth ices over. And this is a little challenging because if the Earth is iced over, it's not clear how it melts again, because ice reflects, if ice is white, it reflects light, and reflected light isn't going to melt the ice. So this is why the polar ice caps tend to stay ice caps over the winter, or even over the summer, because they don't get enough heat because they're radiating most of the heat in the form of light. So the Earth has iced over a couple of times, but then it warms up again. We're not always entirely sure how or why this stuff happens, but each little inflection point here in this graph requires some explanation, has some explanation, and the climate's a very complicated system. So there's lots of things going on here that might explain this various temperature change. So each of these double lines going across are major extinction. Major geological time periods. Yeah. So this is the early Earth between 225 and 65 million years ago. This is the period of the dinosaurs, the Triassic, Jurassic, Cretaceous. This is when the dinosaurs were on the planet. When the dinosaurs were on the planet was a lot hotter than it was today. Much hotter. You need a very hot planet to produce all the really big organisms. When it's cooler, you get smaller organisms. And in fact, the next, so 65 million years ago is the KT event. This is the asteroid that hit the planet and killed off all the dinosaurs, except the ones that survived and turned into birds. And then after that is the period of the mammals. So the mammals are the ruler of the Earth over this time period. And then we're here at the very end. You can see a lot more activity here because we have more data from this period. We have less data further back you go. We have almost no data at the very early Earth. Okay, so this is the next. So what I want to do is sort of gradually zoom in to our current temperature situation, climate situation. So we just looked at the full Earth's history, all 4.6 billion years. This one is just the last 65 million years. So this is just the period of the mammals. 65 million years ago was the KT event that killed off the dinosaurs. So after this period, so you can see here's that sort of cooling trend that we saw in that last slide. Yeah, so on the left here is the temperature change. This is measured with ice cores, I believe. Yeah. Okay, so yeah, so this is the Eocene. Yeah, so we're here at the bottom here, and again, it's a lot more complicated, partly because we have a lot more data, so we know exactly how it's fluctuating in this period. And right now we're on a period of warming again, so we're sort of ticking back up. But you can see over this period we're generally cooling, but not in any straightforward sense. And there's a lot of these sort of weird periods. So there's a period of climate stability that lasts almost 10 million years right here. I mean, it goes up and down, and there's some periods that are warmer than others, but for the most part, it stays in a pretty narrow range, right? That's a stable period that lasted for like 10 million years. Very nice conditions. Then it gets warmer and sort of stabilizes at a little bit warmer period, and then we've been on this cooling trend where it hasn't been as stable. One thing I'd like to point out really quickly is this spike right here. So it's called the PETM. This is the Paleocene-Eocene thermal maximum. So right here at the border between the Paleocene and the Eocene. This whole peak is called the Paleocene optimum. This is the warmest that it got during this whole period of time. But right before the optimum, there was this sort of freak spike in temperature, where temperature changed almost by 2 degrees Celsius, and it spikes up very quickly, and then it just drops back down again, almost by the same magnitude, right? So a 2 degree centigrade spike, and then it falls back almost the same. It goes on to rise again to the optimum after that, but this little brief spike in temperature is very strange. We'd really like to know what caused that spike in temperature. For one thing, that's about the magnitude of temperature change that we're dealing with, at least at the moment, or 1.52 degrees centigrade in this century. The thing is that for us, this temperature change has happened over, like I said, the last about 150 years. The Paleocene-Eocene thermal maximum took about 170,000 years from trough to peak. From trough to peak. So 170,000 years to do that 2 degree centigrade change. we're doing that same magnitude change in about 150 years, so several magnitudes faster. Living systems like stability. They like regularity. If things are regular, if things are stable, then you can plan for the future. Then you know you're going to be around next year, and your offspring will be around the next year. They don't like radical changes in temperature, radical changes in stability generally, because then it's harder to make do. Some creatures can adapt. Some creatures just die off. When you have radical changes in temperature like this, you also have large extinction events. Lots of species who can't hack the change end up dying off. So the PETM is a very clear event in the geological history. You can see the spike in temperature and the effects that it had on the planet. And the temperature, the climate event that we're going through right now is it's more dramatic in the sense that it's happening a lot faster, several orders of magnitude faster. Now, if you don't know the human history, so Homo sapiens only come onto the scene a few 100,000 years ago. The genus Homo only comes onto the scene maybe a 1.5 million years ago. So that's right at the very little last sliver of this chart. This is looking at the last 65 million years. Primates are only in the last little chunk of this chart. And Homo sapiens are at the very, very last sliver. So let's go ahead and dive even further in to look. So this is the last 6 million years. So we were just looking at the last 65 million years. Here's the last 6 million years. Over the last 6 million years, you can see it sort of spikes up and down with a range of temperature. Can we read these as degrees centigrade? I don't remember if we can read these in degrees centigrade. We can read this as degrees centigrade. Yeah, so we have this sort of period of cooling over the last 6 million years. But you have these spikes and troughs, and it sort of goes back and forth where it's hot and cold and hot and cold and hot and cold. Over the last 100,000 years or so, we've gone through lots of these spikes. Yeah, like I said, Homo sapiens are the oldest of our large primate ancestors, are just in the end bit of this 5 million years ago. Homo sapiens have been around for about 200,000 years, maybe 400,000 years, but just in the last little tick of this, 500,000 years is at the extreme end. So Homo sapiens has been around for about 500,000 years, 200,000 years. But anthropologists distinguish between Homo sapiens anatomically and what they call behaviorally modern humans. So behaviorally modern humans aren't just anatomical humans, but they also have recognizable human culture. So they have sophisticated tools. They have clear social practices, rituals, art, artifacts, this kind of stuff. They probably have language. They've mastered certain kinds of art, and they start domesticating animals and so on. So this happens around 80,000 years ago. So we've been Homo sapiens for about 250,000 years. Anatomical Homo sapiens. There have been human beings wandering the earth that are built just like you and me, anatomically indistinguishable from us. But for about the last 80,000 years, 100,000 years, we've been behaviorally modern and recognizably human, wearing clothes and artifacts and this kind of stuff, for just the last 80,000 years. So again, that's just the last little sliver of this graph. This is the last 5 million years, just the last little sliver of this graph. But even from this, you can see that over the lifespan of the primates and also of Homo sapiens, we've had to deal with fairly large changes in temperature. And this looks like temperature changes on the order from 0 to minus 8 degrees centigrade. That's like 8 degrees centigrade change. So Homo sapiens have in the past dealt with large-scale changes in temperature changes on the order of that we're looking at now. In fact, these are the ice ages. So this is the last 1.3 million years before the present. So the present's over here. And you can see what we have here are the ice ages. So here, these are ice ages. These aren't global ice ages, but these are the ice ages that human beings have had to deal with, right? Whereas in just human history, there have been periods where it's been very cold, periods where it's been very warm. And during this period, we Homo sapiens were behaviorally modern in the sense that we had tools and clothes and artifacts, art, language. But we were hunter-gatherers. We were nomadic. We didn't live in any one spot. We sort of moved around, and we had to move around because temperature changed so much that you couldn't settle in any one place because you didn't know in the next year if it would be a viable place to live. So you had to move around a lot, and all the skills that we learned as human beings, we evolved to do as human beings over this time period. Right? These are our evolutionary ancestors. But you can see even in this graph, and I have a better one coming up, that at the end of this is a sort of stable period. This exaggerates the very last little bit. Let me go to a better graph. Yeah, so here's this is the last 100,000. This is just the last 100,000 years. So we've definitely been Homo sapiens throughout this, and we've been behaviorally modern for most of this. And you can see that temperature fluctuates pretty wildly over this period. More than 10, maybe 15, almost 20 degrees centigrade in some cases. But you do see here that for the last about 10,000 years, climate has been very stable, unseasonably stable, more stable than it's been at any other point in human history. Yes, this is my favorite graph here. So this is just the last 20,000 years of human history, or maybe 18,000 years of human history, of temperature change, sorry. This temperature change in Greenland, you can see that it was, for a period it was colder, and then it got warmer. Then there was this brief cold period. This was the last ice age called the Younger Dryas. It's called the Younger Dryas. The Dryas is a flower, it's an Arctic flower, and you see these flowers all over the place during this period because temperatures were so cold that they could grow it sort of everywhere. This is the last ice age. Before this period, saber-toothed tigers and woolly mammoths still were alive. Human beings have populated the entire planet, but we're going around as hunter-gatherers, sort of following the good weather during the Younger Dryas. After the Younger Dryas, about 12,000 years ago, the temperature warms up, climate warms up, and then it stabilizes. And for the last 10,000 years or so, temperature has been extremely stable. It's still fluctuated, right? There's been some cold events, there's been some warm events. But it's been, compared to human history, it's been extremely stable. It's stayed within very narrow range. This has been the Goldilocks period for human history. This is where all human growth comes from, right? Before the Younger Dryas, humans numbered on the order of millions, maybe. But nowadays we number on the order of billions, and all that growth happens in basically the last few thousand years. That's the end here. But the big thing that happens over this 10,000 period is development of agriculture. So climate warms up, climate stabilizes. That means that human beings can stay in one spot, and instead of following the weather, we can grow crops, start domesticating animals, and start becoming an agricultural community. We like to think that we became agricultural because of our big brains, but it wasn't our brains. We had the same brains even before this, and we just had different challenges to face. The reason we have the civilization that we have today is because climate stabilized over the last 10, 12,000 years, and we were able to settle down and start growing crops. In fact, all over the world at almost the same time, human beings started becoming agricultural. And in order to explain this, you might think that people were communicating between sort of the Middle East area and Africa and South America, but it's unlikely that there was communication. What's more likely to happen is just that when things get warm, it becomes easy to do agriculture, and so we did. When we settled down to develop agriculture, we also developed things like writing and mathematics and all the other intellectual pursuits that we have. We also invented money and politics. Right? We have kings and pharaohs and Uh, all of the political arrangements, all the organizing schemes, um, like capitalism, like feudalism, all of this stuff happens in the last 10,000 years because we've been in these Goldilocks climate conditions. Every human language, every human myth or ritual, every story that you've ever heard of, every people that you've ever heard of, every human belief that you know about was generated over this period of time. We have very little cultural knowledge, social knowledge of anything that happens prior to the development of agriculture. Right? This is the beginning of history, written history, where we can actually track what's happening. And the claim here is not because of some enlightenment in human brains, it's because the climate stabilized so that we can do things like settle down and become agricultural. This happens in just the last 10,000 years. Everything about human civilization that you know about happened over this time period. And this period of stability is over. Not just that it might be over, or that if we don't do something about it, no, it's over. We've kicked ourselves out of this stable period. The Earth has warmed up significantly, and we're getting even warmer still. This has caused radical destabilizing events like melting the polar ice caps. Right? The polar ice caps are part of the things that keep the climate stable, and all of these stabilizing functions have been eroded or destroyed. So the brief time period where human beings have flourished has entirely depended on our climate system being stable in this way. And now that that climate stability is over, I mean, we know human beings can survive in unstable climate periods, but not using any of the techniques that we know of. Right? All of the tools and traditions that we have are not equipped to deal with radical climate change. There's a lot more graphs here, but that's really the big point I wanted to make. Let me now just, before I talk about geoengineering, let me talk a little bit about the situation that we're headed into. So this last year, or maybe the year before that now, yeah, in 2015, I want to say, there was the Paris Accords, a big climate change conference. All the big countries and industry leaders met in Paris to talk about climate change. And they made agreements amongst themselves. These were non-binding agreements. They didn't have any penalties for not following the agreements. But they took it seriously. They came and talked about the threat of climate change and what they're going to do about it. In particular, all the big countries there made pledges to what to do about climate change. So this graph will show you the pledges that these different countries made. So China, the US, EU, India, Russia, Brazil, Japan, Canada, Australia, and then all the other countries. I sort of grouped into this last bit. Okay, so this is the graph if we do nothing on our current trajectory. If we stay doing everything that we're doing now with no changes, that includes not letting things get worse. Presumably we're not going to let things get worse, but if we just stay where we are, and everything that we have on path to accomplish right now stays accomplished, if we stay where we are, we're headed for 6 degrees centigrade change by the end of the century, by 2100. 2100 is probably in your lifetime. It's almost definitely in your children's lifetime. Right? This is a live problem that's affecting this generation. 6 degrees centigrade is much different than 2 degrees centigrade. 6 degrees centigrade is we won't be able to plant our crops anymore. Like coffee won't grow, or maybe we can't plant the crops where we do right now, and we have to move everything north. Right, so Canada becomes a farming region, and the equator is a barren desert. Right, so 6 degrees centigrade is a huge deal. It implies radical changes to human lifestyle, radical environmental catastrophes. We're headed for 6 degrees centigrade if we do nothing. But the point of this climate conference was to make some pledges. So they made all these countries made pledges for pledges for 2030, pledges for 2050, and then pledges for 2100. So here are the pledges that these countries made for by 2030. So you can see that the US and the EU both are pledging to cut their emissions, or at least they were at the Paris Treaty. I don't know what the US or the EU is doing right now, but it looks like at the Paris conference they pledged to cut their emissions, cut their carbon emissions, both the US and EU, by almost 90%. It's a big, major cut to their emissions. India, Russia, China don't have the same pledges for 2030, so they're contributing a lot more at this point, right? So, US and EU, Brazil, Canada, Japan, these others have also pledged some reduction in their emissions. So if that goes through by 2030, and if we meet all these pledges, then we're still on path for 5 degrees centigrade climate change by the end of the century. By 2050, the countries have made more significant changes. US and EU have almost entirely cut emissions. China more than half. India not so much. The big trouble is industrializing to the point that you can actually you can actually engineer the changes to the climate. Right? A lot of these countries, China and India, still use coal in a lot of regions, and getting the whole system on new infrastructure is a big challenge. And so by 2050, they will be the largest emitters of greenhouse gases. But if all the other countries keep to their pledge, we're still looking at 4 degrees centigrade climate change by the end of the century. By 2100, oops, sorry. Let me go back to the narrative. By 2100, China, the US, EU, and India have all pledged to cut emissions entirely. And assuming the rest of them haven't made pledges explicit, but assuming that they were on the path that we were looking at 2050, we're still looking at 3 degrees centigrade climate change. By this point, the other countries, which are not on this list, end up contributing the lion's share of climate change. Again, the problem is industrialization and infrastructure. So let me remind you where we are. So this is if all of these countries keep to their non-binding resolutions, and there's no guarantee that they will keep to these resolutions. In fact, Trump has made very clear that he does not plan to keep the US to these pledges. And if the US doesn't say these pledges, a lot of other countries won't either. But even in the ideal circumstances where we keep all these pledges, we're still looking at 3 degrees centigrade warmer by the end of the century. The most ideal path that we have is to 2 degrees centigrade warmer by the end of the century. And that's if everything goes exactly as we'd want it to go. And right, that's not likely. So this doesn't look very hopeful. Because it doesn't look very hopeful, people have become desperate looking for alternatives. And this is where geoengineering starts becoming an option. So this is the Prezi from my friend John on geoengineering. I just wanted to point out a couple of things and read you the word of the day, or the secret word. Yeah, okay, so I'm just going to start a little bit. So usually when you hear about dealing with climate change, you hear about what might be called a mitigation strategy. So mitigation strategy is about stopping climate change before it gets too bad. Things like a carbon tax, cap and trade, something to put extra taxes on people who release greenhouse gases. Like, these are mitigation strategies. This is what scientists have been talking about since the 70s in dealing with climate change. This is what most of the policy discussion ends up being about. These strategies to try to get human beings to behave differently so that climate change doesn't get very bad. Mitigation strategies have almost entirely failed. we really haven't been able to change human behavior. In fact, it's just gotten worse. We're releasing more carbon now than we were last year or the year before that. Right. So if it's not getting better, these mitigation strategies aren't working. It makes people want to look for alternatives. The typical alternative from the conservative political groups that admits that climate change is a real phenomenon. Some political groups still try to, mostly funded by the energy industries, who don't want to deal with climate change. But and the energy industry has known that climate change is a real threat. Their scientists have known it's a real threat for decades, since at least the 80s. But they've, just like the tobacco industries, they've been hiding their science and preventing the public from knowing about the risks because it is bad for business. So you see a lot of people today denying that climate change is a real thing or skeptical about the causes of climate change. Some of these people are in government, right? They're President of the United States. And a lot of the reason for this skepticism is because the energy industry has been funding this deliberately to try to delay doing anything about it. It's literally killing the planet. It's probably going to result in human extinction. But if Deepwater Horizon and all the other engineering challenges have made you worried before, climate change is the big challenge that we need to deal with. We're right in the middle of it, and we still don't know how we're going to deal with it. This is a generational challenge. This is the species-wide challenge. Okay, so of the conservatives that do admit that climate change is a problem, the response, the conservative view is usually not to give government power, or more government power is bad. So instead of giving government power, the idea is to encourage people to adapt. So instead of mitigating strategies, instead of trying to stop climate change from happening, you tell people to adapt and adjust, so that because climate change is happening and you can't stop it, you might as well try to deal with it. Try to get ahead of it and be prepared for it. So like encouraging people to move away from the cities, move away from the coastal cities, move away from areas that are going to be flooded when sea levels rise. Right? It's going to be very expensive once sea levels start rising, but if we can start encouraging people to do it now, then maybe it'll be cheaper. Maybe building new projects, new levees, maybe changing the way that we use land. Not to prevent climate change from happening, but to deal with its effects, right? To adapt to a warmer climate. So adaptation doesn't seem to help the issue. It just seems to get us prepared to deal with it. And the mitigation strategies just haven't been working. So because both of these seem like sort of dead ends, this has increasingly had people looking at geoengineering as an alternative. So geoengineering is operating on climate systems at global scales. So here's the climate system you're going to be working on if you're a geoengineer worried about climate change. This is the carbon cycle. This shows you where all the carbon is located in the geosystem. This is measured in gigatons of carbon per year. So what this is telling you is how the carbon, where the carbon is and how it flows. So for instance, there's 2,300 gigatons of carbon in soil, vegetation, and detritus on land. And of that 2,300 gigatons of carbon, per year, 59.6 of it is released into the atmosphere, and 60 gigatons of carbon is absorbed again by the soil from the atmosphere, by the vegetation. Right, so that's an exchange with the atmosphere of 60 gigatons of carbon per year. 60 gigatons of carbon, that's a lot of carbon. Gigatons of carbon per year exchanged with the atmosphere. Now, the way that this chart works, so same thing, it's the surface ocean exchanges with the atmosphere also. Surface ocean also exchanges with the deeper ocean, with the marine biota, and so on. So the numbers you see here, the black numbers are the natural systems sort of left to their own devices, and the red numbers are human changes to these systems. So the surface ocean has 900 gigatons of carbon. It releases 70.6 gigatons of carbon to the atmosphere, and it absorbs 70 gigatons of carbon into the surface ocean. Right. So just on the numbers on their own, you can see that the flow is slightly more carbon going into the atmosphere than going into the ocean. But here's the human change. Humans, because of human activity, the surface ocean absorbs an additional 22.2 gigatons of carbon into the surface ocean, and it releases another 20 gigatons of carbon into the atmosphere. So you can see that the natural flow is from the ocean into the atmosphere, but because of human activity, that flow is reversed so that the surface ocean is absorbing more carbon than it's releasing into the atmosphere because of human activity. This results in a thing called ocean acidification. The more carbon that's in the ocean, the more acidic it gets. The more acidic it gets, the more hostile it is to life. So ocean acidification is a really big problem. It's part of the reason that our fisheries are dying and all our fish stock are going away. Notice here that the change isn't that big. So the human activity here is on the order of 20, whereas the natural is on the order of 70. It's a fairly wide margin. Human activity is much, much less. But notice the change in flow, right? So left to its own devices, the flow goes one way, and because of human activity, the flow goes the other way. These natural systems, again, they like balance, and when they're imbalanced or when that balance is disrupted, then the system goes wonky. Ocean acidification. One thing to note here is that by far the most carbon on the planet, on the surface, is stored in the deep ocean. 35,000 gigatons of carbon is stored in the deep ocean. Most of that just never gets to the top to get into the rest of the into just the carbon cycle. So this is the carbon cycle. The problem is that all this carbon is in the atmosphere, and the goal is to tweak a system like this in various ways to try to limit the carbon in the atmosphere, to try to limit the impact of climate change. And so this is what geoengineering is about. Geoengineering is about operating on these climate systems to try to trigger climate change. One thing you might do is release more greenhouse gases. And this is the most common form of geoengineering that you hear talked about, these sort of aerosol injections. The idea is that you take like a blimp and go up into the high atmosphere and then release a bunch more greenhouse gases, aerosols, with the aerosol designed to reflect the solar activity so that it doesn't actually get to the surface. One of the reasons this gets talked about a lot, these aerosol injections, right, releasing a big cloud of gas, usually sulfur dioxide, something like that. So you release a bunch of sulfur dioxide. One reason we like talking about it is that we have some empirical evidence of why this might actually work. When volcanoes go off, they release sulfur dioxide. Sometimes some kinds of volcanoes release lots of sulfur dioxide. So in June of 1991, Mount Pinatubo, was a big volcano, went off and released a bunch of sulfur dioxide into the atmosphere, about the same magnitude of sulfur dioxide that we would want to release in one of these aerosol injections. And so because this sort of natural system happened, we could actually study the effects. So you get, so one thing you get is in fact cooling. You do get a few degrees centigrade cooling. You'd want to inject it over the equator because that's where most of the sun is sitting. So injection at the equator will have the biggest impact. And when you inject this stuff over the equator, it actually does cool by a couple of degrees. But it only lasts for a little while until the cloud dissipates, and the way that the cloud dissipates is by falling as acid rain. Right? The sulfur dioxide turns into acid, and then it falls to the ground as acid rain. That increases the ocean acidification, so that's not very good. It also causes major droughts. So this is the drought index in the year after Mount Pinatubo. Mount Pinatubo is on the equator, and what you see is that the droughts around the equator increased quite a bit. You did have less droughts in some areas, but you had more severe droughts, especially in the equatorial regions following Mount Pinatubo. So, Mount Pinatubo, I'm sorry, aerosol injections, they're relatively cheap, and they do actually cool the environment, but they come at a cost of environmental damage from acid rain and severe droughts that affect portions of the planet disproportionately. So notice here that it's around the equatorial regions. Equatorial regions tend to be poorer and less infrastructurally developed. They also tend to be darker skinned, and because they're less industrially developed, they also have less impact on the climate. Right? It's not the fault of South America, Central Africa, and Southeast Asia that we're having climate change. The reason we have climate change is because of North America, Europe, and China and Japan. But right, so it's not the equatorial regions that are responsible for the climate change. But if we do an aerosol injection, they would be the ones who would have to deal with the worst effects from that strategy. But the thing is that you might unleash this on the equatorial regions without their consent. I mean, a blimp like this, I mean, Facebook has blimps that they've been using. Getting that amount of sulfur dioxide, we're talking about a lot of sulfur dioxide, something like 7 teragrams a year. That's a lot of sulfur dioxide, but assuming you can get that much sulfur dioxide, it's not that expensive to go up into a blimp and pump into the atmosphere. And you might imagine, if climate gets really bad, that actors do it unilaterally, right? So if the United States wants to do it, maybe the rest of the countries don't agree that it's a very good idea, but the United States might do it on their own, and then the planet has to deal with the results. And right, part of the consequences is that it doesn't affect the planet equally. Right? Some planets are affected. Some places on the planet are affected disproportionately. How do you make a decision like this? How do you make a decision that'll have a global impact, but that can be carried out by a single actor relatively cheaply? How do you prevent someone from just taking that action on their own? Is it a good idea to do something like that? Are the benefits worth the cost? How do you do that calculation? Especially, how do you do that calculation when the impact is disproportionate across the planet, where some people are going to be more severely affected by it than others? I don't have the answer to this. No one has the answer to this. This is a big unsolved problem. Not only do we not know how to make these decisions, but we don't have any infrastructure. We don't really have any history of making global decisions on this scale. The closest thing that we've ever done on this scale is something like World War II. World War II had most of the industrial resources of the planet devoted entirely to the war effort, right? Devoted to building bombs and weapons and tanks and so on. Right. So for several years, we had the concerted effort of the entire globe dedicated to the project of making a war. We need the same kind of global effort, but this time dedicated to climate change, to resolving these issues. We need to treat it like a war because it really is a war for our survival. But it's a war for humanity's survival, right? The CO2 NASA computer simulation we showed earlier, the carbon doesn't care where the borders of states are. Carbon doesn't care where you build your walls. The climate will go right over those walls. Right, so we have no infrastructure for making these planetary decisions, for making decisions as a global species. We're not organized as a species to make these decisions. We don't have the political infrastructure for doing it. Right, so it's a huge challenge. It's a political challenge. Let me go ahead and make aerosol our word of the day. The secret word for the lecture is aerosol. If you put aerosol into the quiz, you will get full credit for the lecture credit for this week. Aerosol. Yeah, so it's a big challenge, and we don't know how to face it, and it's not at all clear that we will be able to face it, that we'll be able to meet the challenge and actually deal with There's other kinds of geoengineering. So the aerosol injections are one kind of geoengineering. Another kind of geoengineering are changes to albedo. So albedo is the reflectivity of a surface. The more reflective it is, the less it heats up. So the more ice that we have on the surface, the more reflective it is, and so it has a higher albedo, and it means it warms more slowly. So there have been proposals of something like go out and build a bunch of mirrors. Like, if you cover the Sahara Desert in mirrors and have all that sunlight reflected away, will that change the climate? Right? Something like that would be extremely expensive to do, and we don't know the impact it'll have. One problem with this kind of thing is that it's not easily reversible. So if you go out and build a bunch of mirrors and then it doesn't work, are you going to spend all the money to take all those mirrors down? Probably not. Right? It's another big expense for something we already know failed. It's not going to be very fun. One big kind of geoengineering proposal is carbon sequestration, carbon capture on massive scales. And there's a couple of different techniques for doing that. I'll let John talk about all of that. So I'm going to go ahead and stop the lecture here. I'll let you look through the rest of the geoengineering slide and think about different strategies for geoengineering, the pros and cons of these strategies, whether any of them are good. Here's a nice little chart at the very end about different geoengineering strategies, whether they're any good, how affordable they are, how effective they are, and then the size is how safe they are. I'm sorry, the color is how safe they are, and the size is how fast they work. Afforestation is cheap and safe, relatively so. It means planting a lot of trees, but it's the furthest. So things over here are in this corner down here are, highly effective, highly affordable, are both good. Stratospheric aerosols are affordable and somewhat effective, and also very dangerous. But it's the one that's the furthest out in this quadrant, and so that's what makes it a sort of live option that people are actually talking about. These are the other geoengineering options. Yeah, so I'm going to stop there. I hope you learned something from this if you're still listening. Yeah, and I'll be in the Hangout on Tuesday. I'll see you then. Thanks for listening, everyone. Good luck.